Okay, so welcome to this next video in the playlist on group theory. In this video, what we're going to talk about is conjugation in the symmetric group on n elements. Okay, so conjugation in the groups S little n, like so. Okay, so the structure of this video then, what we're going to do is we're firstly going to have a reminder of what the symmetric group on the set of n elements actually is. So we're just going to remind ourselves about the symmetric group on the set of n elements. Okay, then what we're going to do is we're going to talk about cycle decomposition of the elements of the symmetric group on the set of n elements. And then finally, what we're going to then talk about is what the meaning of conjugation actually is in the symmetric group on the set of n elements. And this is really quite nice because throughout this playlist on group theory, when we've talked about conjugation before, it's just been an abstract concept, it's been just an abstract definition, and we haven't really had much intuition as to what it actually means. Finally, in this video, we're actually going to get an interpretation as to what conjugation actually means, and it's a really nice interpretation, okay, but that's the highlight of the video. We'll build up to that. So the first thing that we're going to start off with then is a reminder of the symmetric group on the set of n elements. Okay, so let's start with some s little n, so an arbitrary little n where little n is some natural number, so 1, 2, 3, 4, 5, etc. The numbers you use to count cows or sheep or something along those lines. Okay, right, so remember the way that you construct this group. Okay, you firstly take the set which contains the first little n natural numbers. Okay, so we take the set 1, 2, 3, 4, 5, and it will go on and on all the way up to little n. Of course, if little n is something like 3, then it will not contain 4 or 5, but more generally, for a large little n, of course you'll have these first 5 numbers in. Okay, so it contains all natural numbers up to and including little n. Okay, so we start off with this set of little n elements, and the symmetric group on the set of n elements is going to be the group that consists of a set of elements where the elements are all of the set permutations of this set of n elements. Okay, so as a set, the symmetric group on the set of n elements is going to be a great big set that's going to contain absolutely all of the set permutations of this set of little n elements. So every possible set permutation that exists for this set. Right, so if you like, you can actually view the elements of this set as actually being diagrammatic pictures of the set permutation that they're representing. So for instance, you could actually, if you like, view the elements of the set like so. So here we have the set 1 all the way up to little n, and then I'll replicate it out here. So here is the set again, and you can view the elements of the set then as being a diagrammatic picture of the set permutation. So just listing where every element of the set is actually being sent, basically. So if you like, you can actually view the elements of the symmetric group on the set of n elements as being the actual pictures of the set permutation which they're representing of this set of n elements. After all, this is just a great big symbol. Okay, it's just a load of squiggles on the piece of paper. It's a very complicated symbol, but it is still just a symbol, so you can view that as the element of your group if you like. More usually, however, we will come up with some simpler symbol to represent the set permutation, and we'll put all of the symbols representing all of the set permutations of this set of little n elements into this set, which is going to form the symmetric group on the set of little n elements. Okay, right, so just to remind you how many elements that set is actually going to contain, the order of the symmetric group on the set of little n elements actually turns out to be little n factorial, and the reason for that is if we want to work out how many total set permutations there are for this set 1, 2, 3 all the way up to little n, okay, then what you need to consider is the fact that you can send little 1 onto, 1 here, onto, in total, little n different things. Okay, then if you want to decide where you're going to send little 2, after that there are little m minus 1 places that little 2 can go to. So 1 has little m places that it can be sent. 2, how many places are there left that it can be sent? So for every possibility of where you can send 1, for all of those, there is then m minus 1 possibilities for where you can send 2, because one of the possibilities has already been used up. That's where we sent 1 to. Okay, then for each combination of where you can send 1 and 2, when we come to decide where we can send 3, how many possibilities are there then? Okay, well 2 of the answers have already been used up, so only n minus 2 are left over now, okay, and so on, and you'll go all the way down until you finally get to little n here, okay, and you're deciding now where does little n go? Well, there's only 1 place left over, so there'll just be times 1 there, and that's the definition, of course, of n factorial. Okay, so n factorial is the total number of set permutations of a set containing n elements, basically. Okay, so the order of the symmetric group on the set of n elements is going to be n factorial. Now, of course, at the moment, this is just a set of symbols, potentially very complicated symbols like this, but to make it a group, it needs to have a group composition law defined on it. Okay, so we'll move to that now. So we need a composition law defined on this set of symbols. Okay, and the way that we will define this composition law is that for 2 arbitrary symbols in this set, okay, and let's just call them simply little x and little y, if we want to know what little x composed with little y is, so this entry in the composition table here, and I'm calling my composition abstract composition, so if I want to know what this is, the way that you do it is you firstly do the set permutation associated with this element little y, and then do the set permutation little x. You get a net set permutation when you compose the 2 set permutations together, okay, and that new set permutation you get here, that will be your answer in here. Okay, and this composition table will obey the axioms of group theory because firstly, the first axiom of group theory is that it needs to be closed. It will be closed because whenever you compose 2 set permutations together of a set, you will get another set permutation. So all of the answers in here will be other elements in this set, because remember, all set permutations are assumed to have been put in here. Okay, so it will be closed under composition. Axiom number 2 of group theory is associativity. That, remember, says that it shouldn't matter where you put the brackets if you're considering a composition of 3 things. So if you're considering the composition of 3 things using our group composition law, it should not matter where you put the brackets. Okay, there should be one and only one answer. It shouldn't matter how you associate it using brackets to reduce it into composition of 2 things at once. Okay, and of course we know that this will obey associativity because of the way that we've used composition of the set permutations to define this, and we know that if we compose 3 set permutations together, that has one and only one answer. It really does not matter how you associate the expression, basically, how you put brackets around it, how you break it down into just composing 2 things at once. Okay, it has one and only one answer, and it should not matter at all where you put the brackets, and indeed that's why this composition law defined in this way will obey associativity. Third axiom of group theory, we need to have an identity element. We'll have the identity set permutation in here, and that will compose with any other set permutation to give back that other set permutation no matter which way round you do it. Okay, so that will be our identity element in our group composition law. Finally, inverse elements. For any set permutation that we have in here, there will be it will have an inverse map, okay, and that inverse map will also be a set permutation. Okay, so the inverse of a set permutation is another set permutation, so it will be another element in this set, basically. And when you compose those 2 together, either way round, that will then give the identity map, which we know is the identity of our group. Okay, so indeed, for any element in here, you do also have its inverse. So that's why the symmetric group on the set of n elements is actually going to form a group. Okay, so there's just a reminder of the symmetric group on the set of n elements. Okay, what we're now going to discuss is something that we have never discussed up to this point with regards to the symmetric group on the set of n elements, and this is the topic of cycle decomposition. okay, of the elements of the symmetric group on the set of n elements. Okay, and this is a really important and useful concept. Okay, now, rather than give you the abstract definition of a cycle decomposition of an element of the symmetric group on n elements, what I'd rather do is just show you what this is through an example, because the instant I give you an example, okay, you will get this intuitively. This is a very intuitive concept. Okay, so the instant I show you how to construct the cycle decomposition of an element of some symmetric group on the set of n elements, I hope that you will be able to understand intuitively what this is. Okay, and this has two great advantages. Number one, it gives us a way of naming the elements of a symmetric group on the set of n elements. Okay, and that's probably the motivation to think, have at the forefront of your mind initially, okay, but actually that's not the most important thing about the cycle decompositions. The second great thing about cycle decompositions is that they actually give us a lot of insight into the nature of set permutations, and that is actually the more important thing about cycle decompositions that's going to be really important when we go on to discuss conjugation in the symmetric group on the set of n elements. But initially, probably the thing to motivate what we're about to do, to have at the forefront of your mind, is we're just trying to name the elements of the symmetric group on the set of n elements. It's going to turn out that we get some very nice insight into set permutations from it, but put that to one side and see it later. Okay, right, so cycle decomposition then. As I say, rather than doing the formal definition of what a cycle decomposition is, I'm just going to show you how you actually do one, and I think you'll get it straight away, okay, because it is a very intuitive concept. So I need initially a nice big enough example to work with to make this overt. Okay, so I'm going to take a set permutation from the symmetric group on the set of 8 elements, so S8. So we're going to be working with set permutations of a set of 8 elements initially. Okay, so let me show you the elements that we'll be working with, and I'm just going to make this up. So let me draw out a set permutation of the set of 8 elements. So I'll just firstly write down the set of 8 elements here. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now what I want to draw out is some set permutation of this set of 8 elements, and I literally am just making this up. Okay, so I'll send 1 to 4, I'll send 2 to, maybe we'll keep that on 2, I'll send 3 to 6, I'll send 4 to 5, I'll send 5 to 1, I'll send, where else can I go? I'll send 6 to 3. I'm trying to make it look as complicated as possible. I'll send 7 to 8 and 8 to 7. Okay, right. So I've got some big, complicated looking set permutation of this set of 8 elements. Okay, so we are now going to see how to decompose this element here, and I think I'll colour it in to make it look slightly less formidable. Okay, so I'll highlight it out around with a red box. Okay, we're now going to show how to decompose this set permutation of the set of 8 elements into its cycle decomposition, basically, into cycles. Okay, now as I say, the motivation that I want you to have at the moment is that we're just trying to come up with a way of naming this. So we're trying to come up with a simple way of naming this, and then it will turn out that we get some very nice intuition about this from this way of naming it. Okay, right, so how am I going to store all of the information about this in a simple to look at name? Okay, well this is the ingenious way that someone came up with. Okay, so we start by putting a bracket at the front. Okay, and then you start with the smallest element of the set. So of course the smallest element of the set is 1. Okay, and now I want to store the information of where 1 is actually going to be sent to by this set permutation. And it's going to be sent to 4 in this case, so I'll put 4 after 1. Okay, so I've got 1 and then 4. And note, in my opinion, it would be nicer to have commas here, but the way that people do this is they don't put commas. So you don't put a comma between 1 and 4, you just leave a space between them. Okay, that's common nomenclature. Okay, but if I do put commas in between them, just omit them from your work. I have a tendency to end up putting commas in there, but it's not the standard way of doing it. The standard way of doing it is you do not put commas in between the numbers. Okay, right. Then where are we going to go next? Now let's move to 4 here, and let's put in the information of where 4 is actually going to be sent to. So 4 is going to be sent to 5. Okay, so now I'll put in the information that 4 is actually going to be sent to 5. Then let's go and put in the information of where 5 is going to go to, and 5 is going to go back to 1. Okay, so we do not put 1 there. Instead, what we do is we close the bracket. Okay, and it's now assumed that 5 goes back to the beginning here. So what this bit tells us is that 1 goes to 4, 4 goes to 5, and 5 goes to 1. So we've got a little cycle here of these 3 elements of the set of 8 elements. Okay, and this is why this is going to be called a cycle decomposition. So that stores at the moment some of the information about this set permutation of the set of 8 elements, but it doesn't at the moment store all of the information about this set permutation of the set of 8 elements. So we need to continue on. Okay, so now what we do is we open a new bracket, a new cycle, okay, because these things contained in the brackets are what we're going to be calling the cycles, and hopefully from this picture here you've got good intuition as to why that should be called a cycle. So this is one cycle here, but this element is going to need more cycles to completely describe it. Okay, so at the moment we've got one nice cycle there, but we need more to completely describe this element. Okay, so let's continue on. Now what we'll do is we'll go to the next smallest element of the set that isn't already in a cycle. Okay, so what we'll go to is 2. Now if 2 is already in this cycle, we would then go on to 3. Okay, but 2 is not in this cycle, so now what we'll do is we'll start a new cycle with 2 in it. And we'll ask, where does 2 go to? Well, 2 goes to itself. Okay, so we just end that cycle straight away. Okay, so this cycle just contains a single element, and this tells us that 2 goes to itself. So it's a very simple cycle there. Okay, so there's the next cycle here. Okay. Now what we'll do is we'll go to the next smallest element that isn't already in the cycle. So we've done 1, we've done 2, now we'll go to 3. 3 doesn't appear in any of the cycles we've done so far. So we'll now open a new bracket, a new cycle, and we'll start with 3 here. Now let's store the information of where 3 goes to. 3 goes to 6, so 6 will be the next element in this cycle, and 6 goes back to 3. So we'll close that cycle already. Okay, so there is another cycle that tells us that 3 is sent to 6 by this set permutation, and then 6 is sent back to 3. Okay, and then finally we will have the final cycle. Well, what is going to be the final cycle? I suppose I don't know that yet, but I do know it just by looking at this. Okay, so now what we need to do is go to the next smallest element of the set, 1 to 8, that isn't in one of these cycles already. So we've done 1, we've done 2, we've done 3. We would go to 4, but of course 4 is already in a cycle, so we don't do that. 5, again, 5 is already in a cycle. 6 is already in a cycle, so it's 7. Okay, so we open a new cycle, we start with 7 here, and where's 7 going to be sent? 7's sent to 8. Where is 8 sent? It's of course sent back to 7. So we close that cycle already, and there, that now stores all of the information about our set permutation. It tells us for absolutely all of the elements of the set 1 to 8 where they are sent, basically. Okay, and that is what is meant by the cycle decomposition of this element of the symmetric group on the set of 8 elements. Okay, so that is how you do a cycle decomposition. Okay, now what I want to show you then is I've now shown you how it fulfills the first motivation. Remember, our first motivation was to try and come up with a simple way of naming this incredibly complicated set permutation here. I want to now show you how this fulfills that second motivation, which is giving us a lot of intuition, a lot of insight into the nature of this set permutation. Okay, so I now want to show you how this helps with that, because it does. Okay, so what this shows us, in fact, is that this incredibly complicated looking set permutation here is actually quite simple. It's made up of these cyclic set permutations here. Okay, these cyclic set permutations on subsets of the set of 8 elements. And what this shows us is that actually we can make this set permutation look a lot simpler. Now remember what is actually meant by a set permutation. What is the set permutation on this picture? Which part of this picture is the actual set permutation? Okay, so just going through this, is it this portion here? Okay, and the answer is of course no. That's just the set of 8 elements. The set permutation is of course really all of these arrows, this collection of arrows from one thing to another. That's the information of the set permutation. Okay, so does it matter that I actually ordered all the elements of the set here in this order, going down in numerical order like that? No is the answer. The set permutation doesn't care whether I actually ordered all of these numbers in this nice numerical way. I did not need to do that. So what I'm now going to do is I'm going to reorder the numbers. So instead of listing them down 1, 2, 3, 4, 5, 6, 7, 8, instead I'm going to list them like this: 1, 4, 5, 2, 3, 6, 7, 8. Like so, and then of course I'll need the same listing here: 1, 4, 5, 2, 3, 6, 7, 8. And now what I'm going to do is I'm going to write this exact same set permutation here with the numbers listed in this order instead. And what we're going to see is that now this hideous set permutation over here is going to become very nice and simple when I now show it over here with the orders relisted in this non-numerical order. Okay, so it's going to be the exact same set permutation, and I want to stress that even though it's not going to look like the same set permutation, it is the exact same set permutation, because the set permutation is just the mapping from here to here. Okay, so where does 1 go? Well, 1 goes to 4, so I'll now connect 1 and 4 here. Where does 4 go? 4 goes to 5, so I'll connect 4 and 5 here. Where does 5 go? 5 goes to 1, so I'll send 5 to 1 here. Okay, and that's looking very nice. Where does 2 go? Well, 2 goes to 2, so I'll connect 2 to 2 here. Where does 3 go next? 3 goes to 6 here, so I'll connect 3 and 6. Where does 6 go? 6 goes to 3, so I'll connect 6 and 3 here. And then 7 and 8 just remained in exactly the same position, so I'll just put them back. And can you see, hopefully you agree, that writing it in this way, it looks much, much simpler basically. Okay, this hideous set permutation, just by changing the order of the numbers here and here, we've now made it look much, much simpler. Okay, and here now it becomes much more obvious that really what we have here is just a set permutation that consists of lots of cyclic set permutations on the subsets of the set of 8 things. Okay, so all of these little set permutations that I'm circling in turquoise here, this is a cyclic set permutation on this subset 1, 4, 5. Okay, this is a cyclic set permutation. We're moving 1 onto 4, 4 onto 5, 5 onto 1. This is a cyclic set permutation, and not a very interesting one. We're moving everything along by nothing. Again, this is a cyclic set permutation. We're moving 3 onto 6 and 6 onto 3, and this one as well. Okay, so that is why this is called the cycle decomposition of a set permutation, because we are decomposing the set permutation into cyclic set permutations on the subsets of this set of 8 elements. So we're taking a set permutation that's on this set of 8 elements and we're decomposing it into lots of little bits basically, which are all cyclic set permutations on subsets of this set of 8 elements. Okay, right. So what I'd like to do is do another example of taking the cycle decomposition of an element. Okay, and the next element that I'm going to do, I'm going to do it to motivate the next thing that I want to talk about, which is what it means for 2 elements to be of the same cycle type. Okay, actually, just before I move off this, let's just talk a bit more about general cycle decomposition. So a bit more nomenclature initially, a bit more of the introductory speech. Okay, so the first thing that I want to say is that any element of a symmetric group on the set of n elements, you can construct this cycle decomposition for it. Okay, now, when people write out the cycle decomposition, like so, we usually do not put these brackets that contain a single element, okay, and these are called the one cycles, okay, so we usually do not put cycles that consist of only a single element, okay, so usually people would not write this set permutation like so. Usually the way they'd write it, and I'll put it down here because I don't think I've got enough space there, usually the way this would be written is they'd write the first cycle here, 1, 4 and 5, then they put the 3, 6 cycle, and then they put the 7, 8 cycle, but they'd omit that 2 cycle there. Okay, and then it's just assumed that if you have any elements of the set that don't appear in the cycle decomposition here, that they are just on their own, in a cycle on their own, in a 1 cycle basically. Okay, so that's just the way people do it. They don't bother writing 1 cycles, and then if you have an element missing from all of the cycles that are visible to you, it's assumed that it's in a 1 cycle. Okay, that's just of course nomenclature. Okay, that's not a particularly deep result, it's just the way people have decided to do it. Okay, right. The next thing that I want to say is some more nomenclature, some more vocab, okay, and that's what people mean by the length of a cycle, and hopefully, again, you should be able to guess what the length of a cycle is actually referring to. Okay, so the length of a cycle just means how many elements are actually in the cycle. Okay, so the length of this cycle is 3, because there are 3 elements involved in that cycle. The length of this one is 1, because there's 1 element involved in it. The length of this one is 2, because there are 2 elements involved in it. The length of this one is 2, because there are 2 elements involved in it. Okay, and the final piece of nomenclature then is that we would refer to this one as a 3 cycle. We'd refer to this as a 1 cycle, as I already have. We'd refer to this as a 2 cycle, and this is also a 2 cycle. So people name cycles according to their length. So we'd say that 1, 4, and 5 appear in this 3 cycle here. We'd say that 2 appears in a 1 cycle. We'd say that 3 and 6 appear in a 2 cycle, and 7 and 8 appear in a 2 cycle. So that's just a little bit more nomenclature. I might just put that under here. So we'll have L for length, and then we'll put cycle. So when people talk about an L cycle, that's just a cycle involving L things, or having length L. Okay, right. So what I now want to do then is another example of decomposing a set permutation into its cycle decomposition. Again, then what I want to talk about is what is meant by cycle type of an element, okay, and what it means to say that 2 set permutations have the same cycle type, and this is what's going to give rise to our understanding of conjugation in the symmetric group on the set of n elements. But I think actually we'll have a break here, and we'll do that in the next video.